So let's go over radians and the Pythagorean identity. So we've talked a lot about um, you know angles and circles and with the Ferris wheel and all that. Like those are all very good introductions to really honestly like this is the meat of what we want to like look at in terms of SOHCAHTOA, sine, cosine, that kind of thing. So let's just take a look at what a radian is to begin with. So a radian, if you take a look here, right now this blue line represents the radius of the circle. Now, if I were able to bend and curve, make this radius kind of curve out a little bit, um, I want to see how much space, quote unquote, or what length, arc length, this radius would take up on the radius. So this is exactly what this is just a visualizer, obviously, but it shows us if you take a look. If I were to kind of wrap my radius length, for now it's just this AB point here. If I wrap it around the radius, I'm sorry, the arc of my circle, you can see the length AB has now been curved to be placed onto the circle's outer edge, the circumference. And this is what we define as 1 radian. 1 radian is basically the length of your radius placed onto the length of your circle, part of the circumference. And this is going to be true for no matter how big your circle is. Let's say if I have let's say, since I can't actually see the whole screen, I'll make it smaller. So now I have a radius of 0.3, whatever that unit is. It's still going to fit exactly, or it's going to fit very similarly onto the circle itself. In fact, this length is always going to be consistent, and that should like inherently make sense to us, right? Because we know the circumference is um, is the diameter multiplied by pi, and specifically, if we had a radius of 1, right? If we had a radius of 1, that's the diameter is 2, so 2 pi. In fact, 2 pi would be the radius, the radian amount in a full circle. So that's actually where we get this idea of 2 pi, or I mean, yeah, 2 pi, right? 2 pi in terms of like the diameter, or if we're looking at just half of the circle, the radian would be just pi, just pi. So the radian is actually consistent. There's a 1-to-1 ratio from radian to degrees, meaning that in the same way, right, you measure something in inches, or you measure something in centimeters, or you measure something in whatever, there's always going to be a conversion between one to the other. And of course, there's always going to be reasons to use one over the other. Um, and in the same way, radian and degree, there's going to be reasons to use one or the other as well. Okay, so again, if you want to look at this description, if you want to play with this yourself, that's fine. I'll probably put a link in the description so that you can go to this site. But again, I think it's a very cool visualizer that you can see um, exactly what 1 radian is. And since it goes out, you can see that you can fit about 6.3 or so, which is obviously what 2 pi is. 1, 2, 3, 4, 5, 6, and we have something like a third of this pink line, right? So anyway, that is what a radian is going to be. So like I said, for any circle, it takes about 2 pi length to wrap around the whole circumference. You can kind of think about it as like for any circle, you've normalized the circumference essentially, right? And you can fit with your radius, right? So that you can fit 6.3-ish radius length on there. And so that's going to be, we know that then 2 pi as a unit of measure for angles is the same thing as 360 degrees. So I'm just going to rewrite this here in a full circle. We have 360 degrees. And so we have 2 pi in radians. So 2 pi is equal to 360. What that also means, right, just simply using the fact that 2 pi is 360, that implies that pi is equal to 180, right? Because I can say 360 is equal to 2 pi. Let me divide both sides by 2. I get 180 is equal to pi, right? And similarly, again, I can do the same thing with 180, right? If I had 180 is equal to pi, I can divide this by 2 to get 90 is equal to. Now, when it comes to radians, normally we don't want to use decimals. We don't want to use any weird numbers or anything. Like we want to just use the pi. So we want to keep the pi. We're treating it like a variable, but it's not a variable, obviously, right? It's just a number. So pi over 2 is some number, and this is going to be a much more clean way to represent it rather than, 1 point, blah, 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 right? We don't want that. Just pi over 2 is perfectly fine. And we can do this one more time with 45 degrees, which of course is 90 degrees over 2. Now, instead of writing it as over 2 again, which I can, it's the same thing as multiplying by 1/2. Just it's a little bit more obvious here, I think. So 45 degrees is the same thing as pi over 4. Okay, so that just kind of gives us some entry into the radian world. Now, obviously, we're not always going to work with such nice numbers, right? Sometimes we have to change from degrees to radians, radians to degree. We're going to first look at the former. Now, we can always convert by multiplying by pi over 180, which is the conversion rate, right? In the same way, like 1 foot is 12 inches, we can say 1 pi is 180 degrees. You could use 2 pi as 360, but obviously that's going to reduce, right? This just saves you one step there. So again, I don't know if some of you have used like the picket fence to kind of help you organize your unit conversion. This is one way to do that, right? Whatever I'm trying to get rid of, or so you can come up with something about, right? You can say like, I'm trying to get rid of the degrees, so therefore 180 degrees must be in the denominator, right? Or we can say I want radians, so therefore pi radians should be in the numerator. Either way is fine. Like I said before, and of course, I think what's good about, I think we don't really talk about this as much, but in physics, even, I mean, obviously just in unit conversion in general, right? It's always a good idea to put your units in there because your units will also cancel out the same way that your numbers will cancel or reduce or whatever. This kind of helps guide you to know what you're supposed to have, right? In fact, in physics, it's super important to have your units out. But anyway, um, and like I said before, we don't really want to kind of disturb the pi, just leave it alone. So what I'm going to do is I'm just going to multiply directly across. And what I'm essentially going to do here is to say, well, what does 140 over 180 reduce to? So I'm just going to use my calculator in this case. So 140 divided by 180. Now, if you use decimals, if you use any calculator, normally what they do is they'll give you a decimal, which makes sense. You can change that into a fraction. Right here, you can click on this to get a fraction, 7 over 9. If you're using TI-83 or something like that, there is a functionality. If you go to math, which is right underneath the second button, usually this first option is a little triangle, and it says frac, stands for fraction, just means convert to fraction, right? So you can do 140 over 180, you'll get whatever it was, 0.77777777, right? Then go to math, frac, and then what it'll do is answer. That means converting your answer into a fraction, you should get 7 over 9. So here I have 7 pi over 9. Right, again, because all I'm doing is I'm reducing the 140 over 180, but don't forget about your pi that's still there. We're not going to multiply that pi into it. We're just simply going to leave it there, kind of like a variable, but really just a simplified version of writing it out. Obviously, this is the exact same thing as simply just multiplying by pi radians over 180 degrees. So if you're more comfortable with this, you say the picket fence seems a lot of work in terms of drawing the cross and all that stuff. That's perfectly fine. Multiply directly across like so. Of course, this is over 1 for those of you don't remember that. But if you reduce this, you're going to get pi over 3 radians. So I'm not showing the calculated portion because this should be pretty straightforward reducing, right? 6 goes into 18 3 times. Last is pi radians, 180 degrees. Okay, 85 over 180. I can't do that off the top of my head, so I'm just going to go ahead and do this. But again, using this convert to fractions, I got 17 over 36. Don't forget about your pi. Oops. Now, I also don't want to misinform you. we don't always have radians with pi along with it. Um, Generally, for us, it will be there just as we're more used to seeing radians with pi. But remember, pi is just a number, right? So when we say pi over 3, I mean, that's basically the same thing as, 1 point something radians, right? Because 3.14 divided by 3 is, 3.04 or whatever, right? So like pi over 3 is still a number. We're just saying pi over 3 again because it's what we typically use, right? We're not. It's hard to say like, oh, 1.03 is 60 degrees. Like that's weird. Pi over 3 is just what we tend to use. Okay. I'll leave this page for you as an exercise if you wanted to make sure you know what you're doing and so on and so forth. I will leave you with the solutions. However, 120 degrees is going to be 2 pi over 3. 270 is going to be 3 pi over 2. 30 degrees is going to be pi over 6. Now, even just with this page, I kind of want to show you some connections, right? And seeing how it does make sense between degrees and radians. For example, right here we have 30 degrees, which is pi over 6, while 60 degrees is pi over 3. And pi over 3 is pi over 6 plus pi over 6, or 2 times pi over 6. Same way, 2 times 30 is 60. And again, 120 degrees is just 60 degrees times 2, right? So pi over 3 times 2 is, it is 2 pi over 3. So these two do make sense in terms of how we add, how we subtract, how we take the difference and stuff like that. Like, it's the same exact thing, okay? And similarly, we don't want to just go one direction, right? We want to go from radians to degrees. We're going to multiply by the reciprocal instead, 180 over the pi radians. And of course, we can think about this once again as saying, okay, well, because I want to go from radians, sorry, that was a terribly not straight line. I want to go from radians, that's still not straight, but that's okay, to degrees. So I want to get rid of my radians. Now, they didn't write radians here, but what the pi kind of tells us. So the pi will cancel out, and that's also another reason why we want to leave the pi in there as much as possible, because it will, well, so again, it'll cancel out. But when we convert, if we convert to degrees, it's a nice conversion there. So again, I have basically, this is what I'm doing, is taking 3/4 of 180 degrees, right? Which 3/4 of 180 degrees is 135 degrees. Now I will be, straightforward. I'm not like, I don't do that off the top of my head, although it is possible. I've worked with radians enough to know 3 power 4 is 135. So we'll be working with these good amount. And I think at some point you're going to see pi over 6. Oh, that's 30 degrees. Pi over 3. Oh, that's 60 degrees. And then 3 pi over whatever, right? Like whatever measurement you see, you kind of know what we're looking at, what number we're looking at. Okay, 5 pi over 6, same deal. I can just simply multiply by 180 degrees over pi radians. Again, the pi's will cancel. Again, this is 5/6 of 180. 5/6, or you can say it's 5 times 180 over 6 degrees. And so, of course, this is going to be 150 degrees. And last but not least, with pi over 3, same deal, 180 degrees over pi radians. This is going to give me 60 degrees, which is what we had earlier as well, right? 60 degrees was pi over 3. Pi over 3 is 60 degrees. Again, if you want to try these for yourself to make sure you know what you are doing, this is going to be 120 degrees. 7 pi over 4 is 315 degrees. Now, unfortunately, we just simply don't have the time right now to kind of go over the whole unit circle. It is very nice, I think. A couple things I'll just talk about real quick, right? Notice that, well, I'm gonna take away the points for now. Yeah, I'm gonna take away the points. Okay, but it is based on special right triangles that we just unfortunately didn't really get to go over. But a couple things I want to just kind of point out to you. This looks like a lot of information, but I think what it does is it does a good job of summarizing everything that we talked about. It talks about the quadrants, which in case you didn't know is 1, 2, 3, 4. We're going to come back to this. It talks about the pluses and minuses of each of your I just say if your x and y are positive or negative in each quadrant, right? Quadrant 1, x and y are both positive. Quadrant 2, x is negative, y is positive. Quadrant 3, they're both negative. Quadrant 4, x is positive, y is negative. Okay, and that might be obvious to you, right? And I think it is obvious, but sometimes it's good to remember what your signs are, and in fact, that information can help us generalize something else later as well. Okay, again, if you look at this looks complicated. We can see all the over sixes are here, and you'll notice that they're all pretty close to the x-axis, right? And that's not just intentional, but that makes sense because if you take a look, if I were to draw um, I were to create a right triangle with these sixes, they all share kind of like this common angle almost, right? They all share this amount of angle from as a right angle. I'm sorry, as a right triangle. They all share this angle. Specifically, it's a 30-degree triangle. So you can see this is 30 degrees from where I started. This is 30 degrees to my x-axis. This is 30 degrees from my x-axis once again, and here I need 30 degrees to make that full rotation, right? So that's why they're all over 6. And the next one that I have is going to be 4s. And again, 4s, you can see they're all 45 degrees from my axis, right? This is 45 degrees. This is 45 degrees. This is 45 degrees, right? 180 plus 225 is 45. 315 plus 45 is 360. And similarly, pi over 3, all my pi over 3s are 60 degrees from my axes. And of course, we also have our last one, which is going to be kind of basically our my y, my y-axis here, kind of. I have my pi over 2 and 3 pi over 2. This is my 90, 270. And my x-axis, essentially, where it's not over anything. It's either 2 pi or 0. I don't know why I didn't put 0 here also. And pi. And so this is kind of talk about like why we divided it. Why are these important? So like I said before, we do have the 30, 60, 90 triangle that we didn't really get to talk about. The 45, 45, 90 triangle that we didn't get to talk about as much. But that's really like we use these so often, and they give us these points very nicely. You can see the numbers kind of come up over and over again, just positive or negative. So that's one of the reasons. It's also nice for that these numbers we can count to 360 exactly, right? So let's say I want to count by 30 degrees. Now, in the number system that we normally use in degrees, 30, 60, 90, 120, 150, 180, 210, 2040, 270, 300, 300, 330, 360. It counts very nicely. You can also see that this is in the radians as well. Pi over 6 is here. Another pi over 6 is 2 pi over 6. That reduces to pi over 3. 3 pi over 6 is pi over 2. 4 pi over 6 is 2 pi over 3. 5 pi over 6 is here. 6 pi over 6 is pi, right? I can keep going. 7 pi, 8 pi, 9, I'm sorry, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and then finally at 12 pi over 6, we're back at 360. And this is true for my pi over 4s as well. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. Pi over 3 as well. We have 2, 3, 4, 5, and 6. And finally, pi over 2s, we have pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. Okay. And so these are all very nice ways of dividing up your circle. So you can use them pretty easily, so on and so forth. Now, just one last thing to kind of talk about the unit circle. Like in case, so you can see that in terms of my denominators, it's always going to be 3, 4, 6, or I guess like 2, 3, 4, or 6, right? If you have just the pi over your denominator, it's going to be in the first quadrant. If your numerator number, not the pi, but if your numerator is 1 less than your denominator, you're going to be in the second quadrant, right? 2 or 3, 3 or 4, 5 or 6. If your number is 1 bigger than your denominator, your numerator is 1 number larger than your denominator, it's going to be in the third. 7 over 6, 5 over 4, 4 over 3, right? And lastly, if your number is right under 2, right, as a fraction, right, then you're in the fourth. 11 over 6 is really close to 2, right? 12 over 6 would be 2. 8 pi over 4 would be 2, but you're not. You're 7 pi. I'm sorry, 7. Bad. 8 pi over 4 would be 2, but you're right under that, 7 over 4. Same thing with this, 5 over 3, right? So you, again, I'm not expecting to necessarily memorize this unit circle. I do think it's very, very helpful to know, okay, how do these numbers relate to one another? How do you get all these things? Now, lastly, this is called the unit circle for a reason. If you notice, all of my radius, the obvious radius, is 1. Right? I'm one positive x distance from the center for right here. I'm one negative, I'm to the left distance at negative 1, 0. I'm 1 unit up at 0, 1, 1 unit down at 0, negative 1. So my radius is 1. Now, using that as well as my previous knowledge of all this stuff, I keep not changing this for some reason. I really should have done that. This I meant r, not 1. But remember that from last unit, we said sine is equal to y over r, cosine is x over r. My circle is x squared plus y squared equals r squared. Well, what if I'm on the unit circle? Right? What happens if I'm in the unit circle? Well, that means y over r becomes y over 1. Well, y over anything over 1 is just itself, right? So y over 1 just becomes y. And very similarly, cosine is x over r, but that's x over 1 since the unit circle has a radius of 1. And x over 1 is just itself, once again, just x. And the equation of my unit circle is x squared plus y squared equals to 1 squared, since r is 1. Therefore, x squared plus y squared equals 1. So this is my equation of my circle, my unit circle. So what happens if, because at this point, I know that y is equal to sine, cosine is equal to x. So what will happen if I substitute in sine and cosine? And that's actually what we have as the Pythagorean identity. And this is actually true for all circles, not just the unit circle, but this is true for all. Again, this is what we'll be using a lot for today for your homework, but also just as a notation thing, because I know we haven't really worked too much with this. Cosine squared written out this way is exactly the same thing as cosine theta squared, the way I have written out here. But like I said, mathematicians are lazy. We are very lazy. So we try to not have this much writing in there. So this notation just means the square. Okay, so let's take a look at how we use this. Given sine and given cosine values, show that the identity is true. So all I got to do is to say, well, I know what cosine is. Cosine is root 3 over 2 squared. Sine I also know to be 1/2. And it says show. Now, some of you might not like this. Show is the same thing as prove, like in geometry. So they want me to show or prove that this plus this is equal to 1. So at the end, I hope I have 1 is equal to 1. That's what I hope for. Okay, so let's work through it and see what I get. Root 3 squared is just 3 over 4. 1/2 squared is 1/4 is equal to 1. 3/4 plus 1/4, I wrote this a little bit too low, but that's okay, is in fact equal to 1. So I write this check mark just to show, that's a really big check mark, just to show, hey, like, look, it does work. This is working as intended, I guess, but this does work exactly as I expected it to. Okay, and we're going to be using this, again, this identity a little bit later as well. But again, remember that this is just from what we did here. This is true for all cases. This is essentially like a proof. So it's true for all cases, and you can always use this if needed, right? Now, terminal ray of an angle in center position passes through the point 0.8, 0.6. So they're just telling us the information here. Again, if you're not sure what some of these words mean, terminal ray, right, is it's a ray that goes through, and in center position means from the origin or 0, 0, and it goes through like so. Oh, jeez. Okay, just missed it. All right, cool. Now, from here, it first asks what quadrant is in. As we know, this is in quadrant 1. And they tell me this is on the unit circle, right? So because on the unit circle, my sine value is just whatever the y is. My cosine is just whatever the x is. So sine is 0.6. cosine is 0.8. Again, they want us to show that this is true. So I'm just going to write out the identity for my own sake, because I like to show all my work usually. So sine is 0.6. The cosine is 0.8. Again, I want to show that it's true. So I want eventually 1 is equal to 1. So 0.6 squared is 0.36. 0.8 squared is 0.64. And this adds indeed to 1. All right, so now you don't have this in your packets, but that's okay. I'm going to explain this in just a second. Now, they do tell me that I am in quadrant 1. So all I'm going to do is I would draw this little quick sketch of a graph or a axis, and just draw a line out from your quadrant 1, right? It's somewhere there. We don't know where it is, but that's where it's just a sketch. Okay, and cosine is equal to 5 over 13. So there's a couple things that I know. I know cosine theta is equal to, well, I don't know. I really just, this is all I know, really. Well, no, there's another thing that I know. And I'm looking for sine theta. Okay. However, I do know what's always true is sine squared plus cosine squared is equal to 1. That's always going to be true. So sine squared theta plus cosine, I know, is 5 over 13, has to equal to 1. So I'm going to just start isolating my sine by subtracting 5 over 13 squared. And in order to isolate my sine theta, I'm going to take the square root. Okay, now do note just one small thing. We're not solving for what theta is. We're solving for what sine theta is, right? So once I have this, I'm good to go. So the square root of 1 minus 5 over 13 quantity squared, this is going to equal to 12 over 13. Now, if you need help with this calculation, let me know. But if you had to do this on a calculator, I would put it all at 1, or do 5 over 13, then square it, then 1 minus that answer, then square root it. Okay. Now there's a small problem here, because when you take the square root normally, you get plus or minus. And this is kind of why that plus or minus is super important. We don't know which one it is. And in trig, it is not both. The answer is not both plus and minus. And that's kind of where this chart comes in. ASTC, this stands for, it stands for two things. You're going to remember it as all students take classes, right? That makes sense. All students have, if you're not taking any classes, you're not really a student, right? Now, of course, you can still be a student without, well, anyway, it doesn't matter. This is just an acronym to kind of help you remember. But this stands for all, meaning all trigs, all trig functions, sine, tangent, I don't know why I did not capitalize tangent, and cosine. And this basically means all trig functions are positive here in the first quadrant. Sine is positive in the second quadrant. In other words, cosine and tangent are negative. Tangent is positive in the third quadrant, meaning, again, sine and cosine are negative. While in the fourth quadrant, cosine is positive and sine and tangent are negative. So this kind of helps me to see, okay, is this going to be positive or negative? Since everything is positive in the first quadrant, I'm going to erase my negative choice here. And so my answer for this problem is positive 12 over 13. If you write down positive plus or minus, that is wrong. Okay, that is wrong. Last question, just to kind of show you that we are, what it looks like in different quadrants here. Again, they tell me that I have a ray coming out from in the third quadrant somewhere, right? Off the bat, we already know that tangent is positive, but we want cosine. But that means, you can see here, even here, sine is negative here. Cosine, I expect this to be negative as well, right? So once again, I know that sine theta is negative 4/5, and I'm looking for cosine theta. sine squared plus cosine squared is equal to 1. Sine is negative 4/5. And I don't know what cosine is, and that's what we're looking for. I'm going to start isolating the cosine. And I need to take the square root on both sides. Oops. Okay, and again, if you put this all in the calculator, you should find 3/5 as your answer. But again, this is a negative number because we're in the third quadrant. So I am going to draw in a negative here in a different color just to show where I'm getting this negative from. It's from the chart that I have, from this diagram that I've made. Okay, so that is my final answer, and that's it. Okay, I hope this wasn't too bad of a video. I think it was pretty straightforward. If you have any questions, feel free to come in and ask some questions.